Fermat's little theorem states that if p is a prime number, then for any integer a, the number ap minus a is an integer multiple of p. In the notation of modular arithmetic, this is expressed as, for example, if a equals 2 and p equals 7, 27 equals 128. And 128 minus 2 equals 7 times 18 is an integer multiple of 7. If a is not divisible by p, Fermat's little theorem is equivalent to the statement that ap minus 1 is an integer multiple of p. Or in symbols, for example, if a equals 2 and p equals 7, then 26 equals 64 and 64 minus 1 equals 63 is a multiple of 7. Fermat's little theorem is the basis for the Fermat primality test and is one of the fundamental results of elementary number theory. The theorem is named after Pierre de Fermat, who stated it in 1640. It is called the little theorem to distinguish it from Fermat's last theorem. History. Pierre de Fermat first stated the theorem in a letter dated October 18, 1640, to his friend and confidant Frenicle de Bessy as the following. If p is a prime and a is any integer not divisible by p, then ap 1 to 1 is divisible by p. Fermat did not prove his assertion, only stating, a set proposition est généralement vrai autas progressions et autas nombres premiers, de quoi je vous envoie voir la démonstration. Si je n'apprehende de très trop long. Euler provided the first published proof in 1736 in a paper entitled Theorematum corundum ad numerus primos spectantium demonstratio, in the Proceedings of the St. Petersburg Academy, but Leibniz had given virtually the same proof in an unpublished manuscript from sometime before 1683. The term Fermat's little theorem was probably first used in print in 1913 in Zahlentheorie by Kurt Hensel. Vergederendlich Gruppe besteht nun ein Fundamentals welcher der kleine Fermatsche Satz genannt zu werden pflegt. Weil ein ganz spezieller Teil des Benzuist von Fermat bewiesen worden ist, an early use in English occurs in A.A. Albert, Modern Higher Algebra, which refers to the so-called Little Fermat theorem, on page 206. Further history. Some mathematicians independently made the related hypothesis that 2p2 if and only if p is a prime. Indeed, the if part is true, and is a special case of Fermat's little theorem. However, the only if part of this hypothesis is false. For example, 2341 2, but 341 equals 11 times 31 is a pseudo-prime. See below. Proofs. Several proofs of Fermat's little theorem are known. It is frequently proved as a corollary of Euler's theorem. Generalizations. Fermat's little theorem is a special case of Euler's theorem. For any modulus n and any integer a coprime to n, we have where phi denotes Euler's totient function. Euler's theorem is indeed a generalization, because if n equals p is a prime number, then phi equals p minus 1. A slight generalization of Euler's theorem, which immediately follows from it, is, if a, n, x, y are integers with n positive and are an n coprime, then if then. This follows as x is of the form y plus phi k, so in this form, the theorem finds many uses in cryptography and, in particular, underlies the computations used in the RSA public key encryption method. The special case with Na prime may be considered a consequence of Fermat's little theorem. Fermat's little theorem is also related to Carmichael's theorem, as well as to Lagrange's theorem in group theory. The algebraic setting of Fermat's little theorem can be generalized to finite fields. Converse. The converse of Fermat's little theorem is not generally true, as it fails for Carmichael numbers. However, a slightly stronger form of the theorem is true, and is known as Lemma's theorem. The theorem is as follows. If there exists an is such that and for all primes q dividing p-1 then p is prime. This theorem forms the basis for the Lucas-Lemma test, an important primality test. pseudoprimes. If A and P are coprime numbers such that AP-1 is divisible by P, then P need not be prime. If it is not, then P is called a pseudoprime to base A. F. Saris in 1820 found 341 equals 11 times 31 as one of the first pseudoprimes to base 2. A number P that is a pseudoprime to base A for every number a coprime to P is called a Carmichael number. Alternately, any number P satisfying the equality is either a prime or a Carmichael number.